Hello everyone, welcome to this presentation. I'm Jagdish Mukku, Technical Director at Robin.io. In this presentation, we're going to talk about reimagining the 3-to-1 backup rule for cloud native applications running on Kubernetes. Let's get started. So, the first we are going to look at 3-to-1 rule introduction, and we'll talk about what data protection methods we use generally for protecting the enterprise applications, and then we'll come to Kubernetes data protection and how you can have data protection for the applications running on Kubernetes. And we'll go into the Robin storage architecture on how it provides app-centric data protection. And then we'll have a demo for demonstrating this 3-to-1 backup rule for Cassandra application on running on Kubernetes. So 3-to-1 backup rules was introduced by US-CERT in the paper published with the title Data Backup Options. The rule simply says that there needs to be 3 copies for any data which is important. One is the primary and the other 2 are the backup copies. So in that rule, 3 copies, and the second copy should be on a different media. It can be on-site, but it should be on a different media so that it can withstand the media failure. And the third copy should be off-site. So this off-site can be at a different data center, or it can be in the cloud. So as simple as it is, this data protection, as we can see in the next slides, protects the applications from failures beginning from the node all the way to the data centers. So as we talked about just now, that any enterprise application needs to be protected from hardware failures like disks. Disks can fail from time to time, and in the node failures, the motherboard can fry out, or the rack failure, there might be a power outage for the rack or the entire data center because the data center is in the storm or there's a flooding in the data center. So the second aspect is the manual errors, which happen from time to time, where somebody deletes the data on an error, and we need a way to recover from such kind of errors. And the third is basically malicious activity with a lot of ransomwares, which make the data locked and hostage. We need a way to recover from that particular activity. So as a 3-to-1 rule suggests, there needs to be copies for the data to have data protection for any enterprise applications. So how does the copies, how can we copy data in the enterprise applications? So it can vary across multiple layers of the stack. It can start from the disk level, wherein it can have a RAID. It can have RAID cards or erasure coding to protect your data by providing some copies at the very low level. And then comes to the volume level, at the software level, you can still provide RAID, and also the same thing as erasure coding. And a little bit up, the file system, some file systems provide data protection by replicating data to another disk or to another node. And we have also at the application layer, we have seen with the recent databases wherein they understand the replication, they make copies of the data to another nodes, and they are aware of one fails, how to fetch the data from another node. So all the Cassandra database and mongodb database basically has this kind of replication inbuilt. So next comes how do we protect data from user errors or upgrade issues or reheat data corruption. So we can use snapshots to revert back to a point in time of copy wherein it is good data, and it can make the application running immediately. So snapshot is nothing but a point in time state of the application, and again, it can be done at various levels. like at the volume level. You can take a snapshot at the volume level and file system level, and also the application level. So typically the snapshots are implemented at by the copy on write or redirect on write. Snapshots are typically associated with the life cycle of an application. So an application is deleted, the snapshot also gets deleted. Let's see what is the next data protection. With backups, we can protect the data. This is entirely little different from a snapshot, wherein the backups are again a point in time copy of the app, and they are stored entirely on a different media, different hardware, different location, and it has a different policies, catalogs to maintain the backups, and it has a very independent life cycle than an app, and they form the basis for data protection when the whole data center is gone down, or data is completely gone or corrupted. Backups are used to restore the app, and then disaster recovery, and then if you want to create an apps from the offsite backups for your test or testing your upgrades. All these use cases can be enabled using backups. So how do we take backups? So there are multiple two ways, primary two ways. One is application tooling. The application provides a command to take the backup because it understands the complete data flow and what data, and it maintains the data structures and all the data layout in the disk. It knows how to take the backups, and it can be logical backups or the physical backup. Logical backup or actually the statements like insert statements, create table statements, which are actually stored as a backup instead of the raw files in case of physical backup, where they just dump the MySQL files in the case of MySQL, or in case of SS table files in case of Cassandra. The second way is backup software, which most of us know about. It is infrastructure coordinated. It can generate diffs independently by calculating the checksums, or it can call the APIs of the storage software to know the changed blocks list to efficiently transfer the different the blocks which needs to be transferred. And it may coordinate with the file system, and it may coordinate with it may or may not coordinate with the applications to flush the buffers. So, but one thing is this backup software has much more functionality of managing the whole life cycle of the backups, like policy, when to delete, how many backups to keep, and also it provides a uniformity for all the applications. Even though there are multiple applications, the way the backups are all taken or managed will be in a single interface. So once you have copies through either the mirrors or the snapshots or the backups, how available they are, how can you retrieve them to basically restore from the failures? So typically the storage snapshots are easy to revert. So it takes seconds to minutes. Data mirrors, you don't even know sometimes that the disk has failed because the IO is routed to the disk, the surviving disk. And of course, restore from backup can take anytime between minutes and hours, depending upon where the backups are done and how much data which needs to be transferred back to basically restore your application. So anytime there are copies involved and the restore involved, there are two questions or decisions which need to be taken care of to meet your application requirements. One is, how often does the copy happen? It can happen for every write, or it can happen once a day. So the backup can be once a day, or you can do a synchronous replication for every write. So, or you can take hourly backups. So it all depends upon what your requirements are. So and the second thing is, how long does it take for the application to be restored from that particular copy? So in terms of mirrors, it will take less time. In terms of backups, it's going to take a little bit more time. So it depends upon your RPO requirements and the RTO requirements, and appropriate data protection strategies have to be employed. Let's look at the cloud native applications and Kubernetes. So cloud native application approach is different from the monolithic applications, where the cloud native applications are broken into multiple pieces which can be independently developed, deployed, and upgraded. This gives the agility to all the enterprises. So Kubernetes has become the de facto container orchestration platform to run these kind of applications, because it has a lot of features which basically help in the deployment, automatic rollouts, rollbacks, and self-healing capabilities. So typically an application in Kubernetes looks like this. For example, you want to build a web server. You have a namespace object where all the objects or application will be scoped under this particular namespace, and you have an ingress object wherein it will be a point wherein external traffic is routed to the internal services, and this can be, in this case, it's one service, but there can be multiple services talking with each other, and these services are backed by the pods which is actually running the applications. And if you want a pod is nothing but multiple two or one or two containers residing in the same namespace, and uh, uh, and a pod can use storage. If it's a stateful application, it needs somewhere to write, so it needs a storage, and it is called a PVC, persistent volume claim, and it is provided by the storage class, and storage class implemented by all the storage providers. and and if you want multiple such pods, you can use a replica set to give a count of the number of replicas, and to manage the complete life cycle, you can have a deployment around all these objects. So all these objects are used to compose your cloud native applications, and which can be given to be the Kubernetes API server, wherein it will deploy this application. So let's look at into storage into more detail. Uh, the first thing the applications can use to basically request storage is to the persistent volume claim. So here we'll see a pod which has a containers, and then it needs a volume, and the volume name is my PVC, and claim name is my PVC, and the claim is basically you're asking for a storage request, and this is the size. We have the size of 10 gig, and then this is a storage class name. What this means is we want this storage allocation request to be routed to this particular storage class, and that is what storage class is. Basically, that's it. So this is how you create the pod, and how can the storage classes, the storage providers provide storage. So for example, you want to allocate a volume which 3 copies, and that has to be rack tolerant, right? So in this case, if you allocate all the disks in this particular node of one rack, and a node failure can will result into the application downtime. The same thing for the second one, right? And the yellow one, wherein they're all allocated in the same rack, but if one rack fails, then it is offline. So we want to make sure that the allocations are properly done. So this is the right allocation, where you have storage allocated in each node in one, and only one rack in each. One rack has only one copy of it, so that you can withstand the rack failures. So where you allocate storage matters. So the storage placement is essential for data protection. So the copies needs have a fault domain, and the application should be able to specify the fault domain based on the requirements. And the fault domain can be based on the disk. I just want the disk fault domain, or the host, or host fails, I want to tolerate the host failure, or I want the rack failure, things like that. So how does allocation in Kubernetes typically happen? It happens through the container storage interface. All storage providers implement these container storage interfaces and provide their storage capabilities to the pods who are asking for the storage. So they are used for dynamic provisioning of storage, and also the interfaces also have a way to take snapshots of these volumes, and they can also create clones out of the snapshots, basically creating another volumes with the source as a snapshot. So let's see the components. The CSI is implemented using the 3 components. The 2 components the first component is the provisioner. All the requests for volumes are basically routed to this provisioner, and this is a one per cluster, one Kubernetes cluster. There is one actionable provisioner, and that provisioner is supposed to look at the requirements of the volume request and appropriately allocate storage, which means that the storage can be on hundreds of nodes in the same cluster. So it needs to take a decision on which node the storage should be allocated. The second thing is the external attacher. This is also is one per cluster, and this external attacher makes sure that the volume that is allocated can be basically available on particular worker node where the pod would be running. So, and the last part is basically the CSI node plugin. What that is, for every node, this one is this component is running. So once the attacher figures out prepares the volume for getting attached to that particular worker node, the worker node CSI node plugin is going to make sure that that volume can be mounted on a particular file system mount path, or it's a raw volume. It makes them available to the container. So these are the pieces that the storage provider needs to implement to provide those volume allocation capabilities. So, for example, so if now that we know how we are allocating the storage, how can you protect data with a CSI in Kubernetes? So one thing is by storage replication, which means that a pod might ask for a storage of PVC, and the storage stack underneath, the storage class which implements the capabilities, basically allocation capabilities, is going to have internal replication and give a single volume to the application. For example, the MySQL will need one data disk for its data and logs, and it's going to get one volume. But underneath it, the storage layer can make copies without the pod knowing it. So it can withstand the failures of disk. In this case, it can withstand the failure of the disk, the rack, and still continue to work with these failures. So this is how you give the PVC. So you give the annotations, and the storage class in this case is Robin. So Robin is going to look into the annotation saying, hey, I want the 3 copies, and they have to be host failure tolerant. So this is a fault domain you can use through storage replication. The second way of doing copies is through the application replicas. In this case, the Cassandra and MongoDB, they already know that they have replicas. The application logic itself knows the replicas. So each pod will be placed on different nodes, and they expect that the disks will also be in the same way, so that it can withstand the failures. So the way they are implemented is using a stateful set, and they give the replica set of 3, and within the volume they'll use a volume claim template and then give the sizes. So this is how all the Cassandra and the MongoDB are implemented in one way. So in Kubernetes, what happens? Let's see, there's a pod, and pod uses the storage, which is a PVC. What happens is the scheduler picks a node for the pod to be run, and the allocation of storage is done by the storage class. That is how it happens in Kubernetes, right? So let's see what happens if they don't coordinate with each other. So the pod can be allocated in rack 1 in this case, and this corresponding storage can come from rack 2. And what happens is every time a write or read happens on this particular pod, it has to cross to the rack. And also, let's say if the rack 2 fails, then you have 2 pods which are failed, because the rack 1 pod can't access data, and the rack 2 pod is already gone. So which means that when the scheduler and the CSI doesn't coordinate with each other, then this kind of non-optimal allocations and lapses in data protection can happen. So when both pod and storage class can coordinate, this is what you can the optimal placement happens, wherein you distribute the pods across the racks and you have the storage very close to the pod. And in this way, it can withstand the rack failures, node failures, and disk failures. So this coordination needs to happen between the pod and the storage class. So how does it happen in Kubernetes, right? So Kubernetes scheduler has various phases, and as you see in this diagram, there's a pre-filter, filter, pre-score, score, right? So at the end of each phase, it has an extensible API, which means that it can call that particular API at each phase, and this API can be implemented in such a way that it can take a decision on where these pods can be placed and where these pods cannot be placed. So this is pretty much extensible the way it is done using the scheduler extensions. So one thing is called predicates, custom predicates, which means that the scheduler is going to pick up let's say five nodes in which the pod will be placed, and it gives that list to the extension which a storage class can implement, and that can take a decision that, hey, there is no storage in this particular node, or it doesn't satisfy the data protection needs, so I'm going to filter out the nodes that can't be used for this particular pod, and then return the filtered list. And the Kubernetes scheduler will move on from those filter list to the next cycle. And also, when you are giving multiple nodes, you can rank the nodes based on the scores, basically. So that is one way the extensions, which basically is a storage class, can take extension route to influence the pod placement decisions. And also you have configurable webhooks, which means that whenever an object is admitted into the Kubernetes, it basically an API is called wherein you can act on that particular object. You can add any annotations on that object or any config to this particular objects. And there is pod affinity and pod anti-affinity, wherein you can use these rules to make sure that no two instances can be on the same node. And also there is a volume binding mode, which is basically set on a storage class. What this means is it determines when the allocation request of the volume is issued to the CSI endpoints implemented by storage class. So when a pod and a PVC are given to the Kubernetes, both are executed in parallel. The pod placement and the PVC allocation are done in parallel in the immediate case, basically, right? So, but in the wait for first consumer, the PVC claim allocation is only provisioning and binding is only done after the pod is placed on the particular node. This gives the opportunity for the storage class to pick appropriate storage based on the pod placement. So you have extension points, you have storage class volume binding mode, but if they don't suffice in the placement data protection of your application for your copies, then you can write your own custom scheduler parallel to the default scheduler for the placement of the pods. So the good thing about is Kubernetes scheduler says there can be multiple schedulers that can coexist, which means that you can have a deployment as a stateful set, and you can give a scheduler name is equal to something, scheduler name is something, then only this particular objects are basically given to this particular scheduler. So that way you can write your custom schedulers only for particular certain applications. So let's go to the snapshots. Snapshot is again a point-in-time copy, maintains multiple versions of data on the same media, right? And the snapshots can be implemented at a lower block level or the higher block level. They can be used to roll back your application to a known state of snapshot where you know that everything is working. So let's take an example. What are the challenges of creating a snapshot in the Kubernetes? So that's a very interesting topic. Let's consider this distributed application, which is running multiple pods running on multiple nodes, and they are humming along good. Then we want the ability to take a snapshot every half an hour, let's say, right? So it should result in something like this. So you should make sure that you capture the entire state of the application, which means that the state of the Kubernetes objects and also its data together. Otherwise, if you take the data separately, then there is no way to know which Kubernetes objects it belong to and what order, and all those things comes into picture. Also, so this is what your requirement is. We want to capture the entire application as a snapshot, as a single entity, not multiple bits and pieces. So what is needed for even taking the snapshot of this cloud native application? The first thing is having consistency volume groups. Basically, there are multiple volumes being used at multiple nodes. They needs to form a consistent volume group, and when you take a snapshot, they need to be snapshotted at one single point of time. Otherwise, they are not consistent, and the application may not be coming up if you are rolling back to that particular snapshot. So this would mean that you might need quasing of all the volumes at one point of time. And you need to capture the entire K8s objects which belong to this particular application, as we have just talked about. And also we need to have a capability to run application specific commands to flush these buffers. That's what makes the snapshots application consistent. So the way in Kubernetes you can create a snapshot is basically using a volume snapshot object, wherein you use a persistent volume name, claim name, and then your snapshot name, and you'll get the snapshots. So one thing the Kubernetes lacks at this point is ability to take a consistent volume snapshot, multiple volumes at one point of time. There's no interface to storage class to take a snapshots, multiple volume snapshots in one shot. But it can be done by storage vendor interfaces, something like Robin. We implement a snapshot at application level. So we take snapshot of all the volumes in one shot. So now let's come to the backups. So once you take the snapshot, you can transfer that snapshot to the object store as a backup. So basically, object store, the cloud storage, cloud object stores have become available through multiple vendors now, and they can be used as a target for the backups. So AWS, Google, and Azure has their own object stores, and you can transfer this particular application snapshot to this particular object store and manage the different backups there. And each object store has their own characteristics, and they have their own tiering available within the object store, and they have the capabilities to make it only read-only and things like that. So they form a very good basis for having the snapshots. And also you can use the object store software within the premises to store send the backups, and they're mostly compatible with the well-known S3 API or any other APIs, or they have their own APIs for storing the objects. So let's take an example of this. What else the backups can be used for, right? So the on-premise applications can basically be transferred. Basically, the backups can happen to the object store. Since anyway they are in the cloud, the availability of compute and storage disks available in the cloud makes it enables more cases like disaster recovery, wherein the whole premise is gone. Then you can create the application from this backup on this on-demand compute. And also, if you want to run the analytic jobs or test in DAO, you can spin up an application from these backups in the cloud and enable those use cases. So let's talk a little bit about Robin application, cloud native application platform. So Robin is a software-only solution that sits between the application and infrastructure and translate the application requirements into infrastructure resources. So at the get-go, Robin is built from the application-centric approach. So even the memory, compute, storage is all taken basically has a approach of from the application, which means that any IO which starts at the application until it reaches a particular disk has an application identity associated with it. So this enables Robin to provide app as a service experience to the enterprises. So to achieve such kind of capabilities, we have developed the app over storage, distributed scale out storage. We have the advanced scheduler, and we have the scheduler extensions, as we talked about why it is needed, and other networking capabilities. And we have the workflow automation, wherein all the data management of complex applications like data, distributed databases, network intensive applications are all basically done through a single API. Even though the distributed application is running on multiple nodes, deploying them is a single click. Taking a snapshot is a single click. Making a thin clone is a single click, and taking the backups is a single click. So single click on an API call, right? So this enables as a service experience, and helps in basically the deployment of the complex applications. So let's a little bit to go into more details on the app aware storage. It's basically the design is based on this redirect on write design, the way it writes the IOs, and it enables us to take very quick snapshots for even the distributed applications. And we have a concept called consistent volume groups within for each application, and basically KTS objects, Kubernetes objects. We have what are the PVCs associated with it. We form a volume group, and we take an application snapshot of those particular volumes in one shot. And also all snapshot, as we talked about cloning, backups are all application aware, and snapshots and backups, they contain the entire state, which means that it has the Kubernetes objects, all the Kubernetes objects associated with this particular application, and all the PVCs and their data is all captured in one shot and associated with the one unique identifier. And we have the QoS guarantees, and then to limit the IOPS or provide the increase the IOPS, basically since the application-centric approach is used and identity is used in all the objects, so we can provide application QoS guarantees for it. And Robin brings data management to the Helm applications. You can install your Helm chart basically, and then give that application, register that application to Robin, and Robin is going to add data management capabilities to Helm applications. Also, the Kubernetes objects, it helps. For example, it's a stateful set. You can you can register that stateful set to Robin as an application, or anything for that matter, like a collection of objects with particular labels as one application. And Robin is going to consider that as an application and provide all the snapshot, backups, and clones management capabilities for such kind of applications. So the layout for Robin is basically a volume is a logical divided into logical 1 GB slices, and each slice is basically comprised of multiple 32 MB physical segments, right? So only a write can actually trigger a segment allocation, which means that if no write has come, then no physical storage is allocated. That's what makes it thin provisioning. And within the segment, basically we use a log structure format, and every write, even the overwrites, go to a new location. So this is a redirect and write approach, and every disk is basically divided into multiple 32 MB segments, and when a write comes from the volume, it figures out where the slice is. A slice can be coming from any other node, and each node will determine if there is already an existing segment to basically write this data. Otherwise, it will create a new segment. So each segment has an identification, like which snapshot it belongs to. So this is how it becomes easy, basically simple to change the view of the volume. So if you want to roll back a volume to a particular snapshot, the segments can be views can be the volume views can be changed to only consider these particular segments, and it becomes a that particular volume snapshot data. And if you want to take a backup, these segments are moved to the cloud. So, and also associated metadata is moved to the cloud. These segments form the basis for implementing the snapshots and the backups and then the clones. So to summarize, there is the 3-to-1 backup rule. One is to make an on-site copy, you can use either application replication, where the application is taking care of its own replication, or you can use the storage vendors, the storage providers replication, where it replicates the data. But in both the cases, the storage placement matters for data protection. Right? They have to basically adhere to the data protection requirements. So that is where the scheduler extensions, all those things are needed. The second thing is snapshots for quick recovery. When there's a manual error, you want to be able to revert a application to a particular known state, maybe half an hour back. Sometimes bringing the backups and restoring the whole application takes a lot of time. Having snapshot gives you a quick capability to revert back fast and make the application online. And for taking such kind of snapshots, you need consistency volume groups. So the third thing is, for the third copy, you want the backups to be in the cloud. So which means that the backups have to happen like snapshots at the application layer, which means that the backup has to capture all the Kubernetes objects, its state, and also all the volumes data. And the transfer should happen very efficiently and in a compressed way, and then encrypted when it's going to the backups. So let's come to the demo part. In this demo, we are going to basically run a Cassandra application using a stateful set, and we are going to show that when that application is deployed, its storage is coming from multiple nodes, and it basically can survive the node failures. And we'll take a snapshot of the application, and we are going to simulate a user error, and we are going to use that snapshot to revert back and restore that particular data. And the third thing we'll show is basically take a backup and backup to the basically AWS S3 object store, and we'll simulate an error like deleting the complete app, and we'll use that particular backup to restore this particular application. Okay, let's look at the setup details. So in this Kubernetes cluster, we have one master and 3 nodes, and we have the storage class as Robin as default. So the volume binding mode as wait for first consumer. All the PVC allocation requests are going to be routed to this Robin if the storage class is not given. And let's see the Cassandra application. We are going to use a stateful set, and we are going to pass a hint to the Robin the storage class, saying that I want a storage infinity to host. What this tells is we want the storage to be allocated on the same node where the pod is placed. That's what storage affinity is. And we're going to use the pod anti-affinity, which means that no two pods of Cassandra should basically placed on the same node. We want them to be on a different nodes. And we are going to deploy this in this particular namespace called prod. So, okay. First, we are going to create a service. Okay, I just created on a default namespace for. So let's delete this, and we're going to say nprod. basically I'm going to deploy in the namespace prod, and the same thing is going to happen for Cassandra. We just saw it. So kubectl get all minus n prod. So the container is getting created. So it's going to take a little while for all of them to come up. Let's look at the status. So they're all up and running, and we're going to do the Cassandra status. So it's all up and normal. So now let's make sure that the pods are allocated on different nodes, and its corresponding data is stored on different nodes. So this is a command which says that this pod is running on this node. So all these nodes are in different thing. Now let's see if the PVCs, this PVC should be coming from 9571. So this can be known by using Robin volume info and basically so hi. So there was some old PVs there. So they interfered with the test. So what I did was I created the service Cassandra and the Cassandra again, and I waited until the node stool status is up and running, up and normal. And now, as you can see, the pods, where are the pods allocated using this command? To see the node name, we have Cassandra 0 is on 46, Cassandra 1 and 96. So three different nodes are used, and each pod is basically on one node, and they have pod anti-affinity. And we let's see if this pod's PVC is coming from its own node. So this Cassandra 0 is on PVC, this one 28, and if you see the volume, Robin volume info, it says that it is allocated from 1995-46. It's the same node as that of where the pod was. Similarly, for other volumes also, we have this. So, which means that all the pods and the storage are coming from the same node, and then they are no two pods are on the same node. So this gives a data production. So let's insert some records into this database. So this is a small script which is going to create a key space and then create a table and create some entries into the database. And then we are going to, after this, we are going to inject some error. But before this, let's do the so it inserted some records. So these are the records which are being used, and we can see what records were. So these are the records which got allocated. So now we have some data in the application. Now we are going to create a snapshot at this point of time. Before that, we have to register this particular stateful set to Robin so that it can create a snapshot of the entire stateful set, which basically is the Cassandra application. So to do that, basically you need to give a label selector saying that app Cassandra, and it's going to pick up all the objects. So before it can register, you can check what are the objects which are being picked up by this selector. So once you know these are the objects which form the application, we can basically create an register this particular objects to Robin with name Cassandra. So once it's given, we have the Robin basically tracking that particular Cassandra application, and we don't have any snapshots or backups. So Robin snapshot create, snap name, and then snap one, and then we give what is the application name, and then we have to wait. And it's going to create a snapshot at this point of time. All the KTS objects in the PVC volumes are getting snapshotted in one shot, and it's all captured in one identifier. So the snapshot is created. Let's see the snapshot list. So we have this particular unique identifier, which is taken with the name snap1, right? Now we have a snapshot. Let's simulate the user error by deleting the data we just inserted, right? So we have select star executed before. Yeah. So these are the objects. We are going to truncate this table. And let's select star to see if we actually truncate the table. So we basically have user error, basically deleting the records, but we have the snapshot, so we can restore this application from this particular snapshot. So let's give this snapshot ID, and the app name is Cassandra, and then we wait for it. So this is a single command, which is basically results in an API call to the backend, which basically does the whole job of reverting the entire Cassandra database distributed application, which is running on 3 nodes. It's going to take a little while. Okay, so the restore is done. Let's make sure the data is back. Yeah, so here we don't have data, and when we restore back, we see the data back. So that's how we can restore your application from the snapshot. Now we are going to see how you can take a backup of this particular snapshot to the AWS object store. So I have already registered a repo, basically, which basically says that it is the AWS S3 with the bucket of this name, and inside the bucket, this is the path, and all the backups are going to go within this bucket path. And we don't have any backups created, so let's create this backup. Robin, before that, we need to attach the repo to an app, so we'll do that. So I attached the repo to the application Cassandra, which means that it can take backups to that particular repo. Let's create the backup using this particular snapshot ID. The name of the application is Cassandra, and then this is our backup target. So it's going to take some a while. Robin job wait 216. So the backup is done. Let's see the backup ID here. So we have the backup ID, which is taken from this particular snapshot. So now we have the backup in the cloud. We are going to simulate a user error or a corruption by actually deleting the entire application from this particular namespace. So in the interest of time, I'm going to do that in the background and start the recording. So I have deleted the app. Let's make sure that we have So there's no Kubernetes objects in this particular namespace, and we have no PVC in this particular uh, namespace, right? But we have the backup available, so we should be able to restore the app into this particular namespace. Robin app create from backup. So you can see even the Robin app doesn't exist, so we delete the app. So Robin app create from backup, restored app, and we give this backup ID into the namespace prod, and then we'll wait for it. So this is going to take a few minutes. So let's look at the status. So they're all up. Sorry, get pods, and they're up running in the last 2 minutes. So the app is basically created. Let's look at the data. So basically, if there's data, so we have our data back. We create the app from the backup. So in this demo, we created an app with application protection with 2 copies in the on-site. Then we use the snapshot to restore the app, and we use the offsite copy in the 3-to-1 backup rule to restore the app. This concludes the demo and the presentation. Thanks for watching.